and I'm a PhD student partly at the University of Groningen and partly at the University of Aix-Marseille. And today I'm going to talk about, can you increase motor flexibility through learning? What actually is motor flexibility? Well, motor flexibility is the fact that you can accomplish a goal in a task with different joint angle configurations. And high flexibility can be very necessary in daily life. If you, for instance, want to hold a cup and you're walking, then it's nice if you can change your joint angle configurations to keep the cup of coffee in a good position that you don't spill. And it's also good for perturbations and to handle task constraints. And if you have low flexibility in daily life, it might give problems, because then if you walk with the cup, you might spill. And there are several patient groups, like stroke patients and Parkinson's patients, which have low flexibility. If you want to understand flexibility, motor flexibility, we propose that we distinguish in two types of variability, which is goal equivalent variability and non-goal equivalent variability. And the variability is the variability of the fingertip and the variability of the joint angles. And we see this as not as a different strategy, but as a coordinative solution. Goal equivalent variability is the variability where you reach the goal. So to reach the goal and to stay at the goal, you can use different joint angle configurations. This is not only possible at the goal, but also during the movement. The second type of variability we have is non-goal equivalent variability. That is when you miss the goal. So you also have different joint angle configurations to miss the goal. And also during the movement to get away from the mean path of the end effector. To quantify motor flexibility, we use the uncontrolled manifold method. And the first thing we do in this method is select a performance variable. And the performance variable we think is controlled in our task is the fingertip position. And this is controlled through the elemental variables, which are the joint angles. And of these two, we make a linear geometrical model. And when we've made that model, we can partition into the two types of variability, the goal equivalent variability and the non-goal equivalent variability. Here you see how we distinguish in these two types of variability. Right. The two parts on the right, you can see that the end effector is on one spot and that there are different joint angle configurations possible. And the one that's the goal equivalent variability. And on the left, you can see the non-goal equivalent variability, where the end effector is not at the goal, these have different joint angle configurations. You can see that this goal equivalent solution can be shown in a line, and then the two on the right are on the line, and the one on the left, which is non-goal equivalent variability, is not on the line. We think that the measure of motor flexibility is the ratio of the goal equivalent variability and the non-goal equivalent variability. So if we want to come back to our definition again, this was the fact that the same action goal can be accomplished with different joint angle configurations. And it was necessary in daily life to have high flexibility, and low flexibility can give problems. So what we wanted to look at is it possible to increase motor flexibility over learning? If you look in literature about learning and motor flexibility, there are a kind of inconclusive results, and there's not really much attention, and there are different scenarios for different tasks. So it was for us difficult to develop literature-based expectations. We use a point-to-point task, you can see here, to do our experiment. And what we thought was an idea how you can increase motor flexibility is the fact that you can make people exploit different joint angle configurations during training. So this is the left picture. You can see a person from the frontal plane, and this is the shoulder and the elbow and the wrist and the finger. And you can see that there are different joint angle configurations when the obstacle gets higher. If you look at the black one, it's different from, for instance, the blue one. So we thought if we do a task with an obstacle, and we take one basic obstacle and we do an intervention with different kind of obstacles, then the people would exploit several different new end effector paths and joint angle paths. And we thought this would result in more motor flexibility because the Go equivalent variability would increase and the non-Go equivalent variability would decrease. This is again the task we did, and the idea that we had a basic obstacle at the beginning and several different obstacles in between, and not the basic 10 centimeter obstacle, and a post-test with, again, the 10 centimeter obstacle. We had an intervention of 600 trials divided over 3 days, and when we did the analysis, we only analyzed the baseline 30 trials of 10 centimeters and the post-test 30 trials of 10 centimeters to see whether there was an increase in motor flexibility. The instruction we gave the participants while doing the task was that they had to be accurate and as fast as possible. What we found in the Go equivalent variability, at the y-axis you can see the variability, and at the x-axis you have at the left you have the baseline, and at the right the post-test. And the light blue is the Go equivalent variability when the fingertip is just above the obstacle, and the dark blue is at the goal. And you can see that there is a slight decrease in Go equivalent variability after the intervention. The non-Go equivalent variability, the graph is exactly the same as the left one, only there's the non-Go equivalent variability on the y-axis. And you can see that there is some change, but it's not a significant change in non-Go equivalent variability. These two, the ratio of these two variables is the motor flexibility. So the motor flexibility is on the y-axis of the left graph, and the rest of the graph is built up like the last one. And you can see that there's some change, but from the pre-test to the post-test. But if you look at the individual data, which is on the right graph, the baseline is on the x-axis, and on the y-axis there is the post-test. And if there would have been an increase, all the dots would have been above the line. And as you can see, this is not the case. So we did not find a change in motor flexibility. And then we we got inspired by Freitas because they did find an increase in flexibility in a different task. They did a target jump task, and they saw that when there are target jump tasks in between, that the non-target jump tasks has an increase in flexibility. And we wanted to take the same design, but then in our tasks. So what we did was do all the 10 centimeter movements within all the other obstacles. So we tested whether the motor flexibility would increase when the 10 centimeter obstacle is in between all the others. And again, we expected that the motor flexibility would increase because the Go equivalent variability would increase and the non-Go equivalent variability would decrease. So we did a baseline test with 30 trials of 10 centimeter movements again, but the intervention included the 10 centimeter movement. And again, we analyzed the 10 centimeter movements to see whether the flexibility would increase. At the left you see the same kind of graph again as you saw before, and you can see that there seems to be an increase in goal equivalent variability, but this increase is not significant. And there also seems to be an increase in non-goal equivalent variability, and this one was significant. But how do these two come together as the mode of flexibility? So the ratio between the two was the mode of flexibility, and did that change over time? In the graph on the left you can see that there might be some change, but not really in one direction. And in the graph you can see that they're mostly near the line where it stays the same. So again, we did not find a significant increase in mode of flexibility. So the conclusions of our two experiments are that in the first experiment we did not find an increase in mode of flexibility, that there was slightly less goal equivalent variability, and that there was no change in non-goal equivalent variability. The second experiment showed again no increase in mode of flexibility, no change in goal equivalent variability, and a slight increase in non-goal equivalent variability. What we were thinking of, maybe the task is too overlearned, and the extra flexibility is not really needed to do the task. But again, we thought, yeah, we still want to increase this, somehow want to learn something about how to increase mode of flexibility, because there are patient groups with a low flexibility, so we want to get some kind of grip on how we can increase this. So maybe we should use another different task. And we thought we are thinking about doing future experiments with different tasks where more exploration in the joint angles is needed during the task. And the upper task is an idea that you the joint angles will result in a different end effector, which is a virtual end effector, but then the movements of your limbs won't result in change in the end effector like this, but on a screen it would go differently. So you really have a new task where you really have to explore what happens if you move your limbs and and it would be interesting to look at that, how it evolves over time, and if mode of flexibility would change over time in this new task. And the other task we're interested in is an interception task. It is interesting to use because you can really push the system kind of to the max, because you can make the balls fall very, very fast, and then people have to move really fast, and they really exploit most of the options there are. So we're really interested in what will happen in mode of flexibility if you do that in tasks where more exploration is possible and is more exploration needed to accomplish the task. Are there any questions?